We are moving on through our semester. We are now at 11B. In this lesson, we will derive the symbolic or algebraic form of the deer population logistic model. The concepts and explorations will provide insight into how mathematicians investigate numerical data, such as carrying capacity and logistic growth rate, to find a symbolic representation of the model. During this activity, you're going to need to have your work from lesson 11A, 11 part A for reference. So starting with question 1. Again, this is a great time to hit pause, go work on these by yourself, and then come back and let's work on them together. Look back at your sketch from lesson 11 part A. Question 5 part C. When was the growth rate at its lowest and when was the growth rate at its highest? So looking at this graph, it asks on question 1, when was the growth rate at its lowest? So this area right here is an area when our deer population is not growing very much. And also up here is when it is leveling off. So the when is around 1980 to, around 1996-ish. It depends on how you want to call that. That's there. And then it does seem to take off from there. And then back on this side, somewhere in the neighborhood of 2012 to a predicted 2030, this area looks like it's very slow on its growth rate. But then it says, when was the growth rate the highest? And from about right here to about right here, around 2002 up to whatever you'd like to call that, 2008, there is a spike in the growth rate. So in this lesson, our objectives are that we'll understand logistic curves and symbolic models and how they can be used to approximate some real-world data. A logistic model uses historical data to determine the parameters carrying capacity and logistic growth rate. You're going to be able to develop discrete models of natural phenomena, and you're going to be able to use those models to predict future values. And we're going to be able to calculate the carrying capacity and the logistic growth rate of a real-world scenario. Question 2, go ahead and hit pause, take care of business on question 2, and then come back and let's work it together. In the Lesson 11 Part A activity, you analyze the data to create a graphical representation. In this activity, you're going to use the data to create a symbolic representation. You will determine the parameters of a logistic model that best matches the data. Getting started with Part A, what was the estimated carrying capacity for the deer on Smith Island? And we're going to call this amount, I have some picture missing here, L. So L from our past lesson was 1,584 deer. Recall that in 1996 there were 30 deer. This number represents what percentage of the total carrying capacity, and round our answer to the nearest whole percentage point. 30 is the part out of 1,584 deer. That's the whole. And grabbing a calculator, I am going to do 30 divided by 1,584. I'm going to multiply it times 100 to get from decimal to percent, and to the nearest whole percentage point, because my screen is showing 1.8939, blah, blah, blah. But to the nearest percentage point, that's 1. The 8 says we're at 2%. In 1996, what percentage of the carrying capacity remained? Okay, hang on. If the total carrying capacity is 2%, then what amount is going to remain? Well, the island has 100% capacity. If in 1996, we've used 2% of it, then that means how much remains? 98% remains. Then it says, let's let P sub t represent the population of deer at time t. Show the calculations we were just talking about on part C using the variables L and P sub t instead of numbers. Okay, no problem. The only thing is we're not going to use percent, we're going to use decimals. And so I'm trying to convert 100% minus 2%, and they want us to represent our calculations using these variables. Okay, instead of 100%, I'm going to use 1. And you're noticing we're going somewhere with this, and it's going to be one of our formulas. And then this 2%, the 2% came from here, which came from here, so let's represent this fraction. The numerator is 30. 30, that was the number of deer. And so they're asking us to use P sub t as the population of deer. So we'll put P sub t over. And then this 1,584 represented the carrying capacity. And so what does it ask? Where are we? P and T and L. And I don't see where they're telling us about L. It just says to use these variables instead. Maybe they defined it earlier and I'm just forgetting about that. But L is going to be our carrying capacity. And so that is here. So making this a little bit more clear, we have created we're using letters instead of numbers, and then we're going to keep on going. So now very slowly and calmly and methodically, we're going to put all of this together and create a formula. As you saw in preview 11b, when studying two discrete points in time, relative change in a population can be expressed as the change in the population over an original population, and this is called the growth rate. In a logistic model, the growth rate at time t, and I'm kind of glad I've got stuff missing, is proportional. Okay, whoa. The growth rate at time t is proportional to the remaining capacity. Growth rate is proportional to the remaining capacity. The constant of proportionality, got to be in there somewhere, if we're proportional, is K. Whew, what we know so far, this change of P over P, that is called our growth rate. That relative change in the population can be expressed as, and it says, this growth rate at time t, this growth rate, it is going to be proportional to, that means there's a K going on, our constant of proportionality, to the remaining capacity, Remember what we just did a while ago? We had like our 25%, but then we had to do 1 minus, or the 100% minus, and it ended up like 75%, blah, blah, blah. In other words, we've got 1 whole minus the percentage of our carrying capacity that we have used, and then it's going to be what is remaining. But wait, there really is more. The growth rate amount, in other words, the absolute change, the delta P. So these are huge words we have been talking about all semester. Relative change, he has a pretty new face here. And absolute change has a pretty new look too. But somehow the K is still over here. Now there's a P over here, and we still have what it says, the remaining capacity. Part A keeps going and says, how in the world was the second formula developed from the first? And if you have not stopped and answered that, it's the time to stop and answer that question. Because if you let your eyes go back and forth like a tennis game or ping pong or something, you're going to be like, well, This piece is the same. This piece is the same. The only thing that's different is what used to be stacked is now split apart. So if I could multiply this side by p and multiply this side by p, these would reduce to become 1. And my delta p would go here. I've got to make sure I'm multiplying a p over there. Oh, so we just multiplied by both sides by p to isolate the change in p, which is delta p. But then part B says, let's look at two special situations. Two special situations when P is worth 0, and then when P is getting close to the carrying capacity. They're asking us to look at the right-hand side of the formula, and that's the delta P over P. I'll provide this on the test, but sometimes it's just really good to go ahead and memorize stuff because then you know that you know that you know it. But here's our formula. What's going to be the value of the change in P over P when P is 0? Oh, and so that's the question. And so let's calculate it. What is going to be, and it's the formula, well, I've already read it, it's rewritten right here. What's all of this going to work out to be when P is 0? So delta P over P is worth K times 1 minus P over L. And the only thing they're giving us is, let's let P be 0. So I get a constant times 1 minus 0 over L. Well, 0 over L becomes 0. 1 minus 0 becomes 1. And K times 1, well, it all just turns to be the constant of proportionality. Something to note in your notes. When the population is 0, then our change, our growth rate, our change in P over P, our relative change, is just K, the constant of proportionality. Make a note of that. So you're doing great. Remember, you can always hit pause, go back and re-listen to something, rewrite something, but don't move on if this lesson is still foggy in your mind. Make sure you've completed parts C and D. We're about to do them together. Looking at the right-hand side of the formula, so we're at that delta P over P, K, constant proportionality, equals 1 minus P over L. Looking at the right-hand side, what will be the value of the change in P over P, the relative change, when the value of P, the population, approaches the value of L? And in your own words, explain what's going to happen to delta P over P. Think about it. Play around with it. And I'll play around a little myself. So the question is focused on this part back here. What's going to happen when P approaches the value of L? And a while ago, the carrying capacity was 1484. So P could be 1480, then it could be 1580, 1581, 1582, 1583, 1584. And we can keep playing around to see what happens with that, but let's just go ahead and say it made it. It equals it. So we know that L is the limit, it's the carrying capacity. And the formula is supposed to be P over L, but let's just get rid of the P and say, hey, P finally made it. It equals the L. Let's see what happens to the right side of our formula. So we get K times, let's see what's going on in here. Inside of here, L divided by L is just 1. 1 minus 1 is 0. K times 0 is 0. The whole side is going to turn into 0 as the value of P, the population, approaches L, the limit, the carrying capacity. The population, this change in the population, its growth, its relative change, it can't grow anymore. Part D, in the real world, it is possible for the population to exceed the carrying capacity. Models provide projections and are usually not precise. When P, the population, is greater than the carrying capacity, What does that tell you about P over L and about 1 minus P over L? Another question, what would it mean with regard to the change in the population? Again, take time to hit pause, think on this, and then come back and we'll talk through it together. So when P, the population, is greater than the carrying capacity, then that means this P over L is going to be greater than 1, which that means that negative, well, this 1 minus something larger, this whole thing is going to be negative. And if all of this is negative and we're multiplying it times the constant of proportionality, then we can expect to have a negative growth rate the next year. The population would trend back down toward the carrying capacity. And if you think about our graph a while ago where we had the carrying capacity and then our graph was spiking up, it may go above carrying capacity, but it'll have to drop below it. It may go back up and then down and then back up. So it's going to be a cycle of going above and below the carrying capacity. That ends our lesson, but before you head off to do your practice assignment, I want to point out that, remember, you have spreadsheets in my math lab. This is lesson 11B, so we'd click on 11, you have to open the zip file, then open the file itself, and then you would find 11B practice. The thing I wanted to point out has been confusion for students in the past, and I just want you to notice there are bottom tabs on the spreadsheet. This one's called Delta P. This one's Delta P and a graph, and you can play around with the graph by changing these numbers, and then the United States population. So before I let you go, I wanted to explain the bottom tabs on your spreadsheet for the 11B practice. This does conclude our lesson 11B. Check your syllabus, see if there's more to do. Make sure you do your homework. I'll see you again.